Let's revisit the logistic equation that we introduced in the last section. I've put the phase plot in the notes. The way I got the phase plot was by putting in some numbers for the constants. I don't remember exactly what I put in. I had to fiddle around with them a little bit to get a graph that was easy to screenshot. I think I put in 1 for R and 10 for K, but I don't honestly remember, and it really doesn't matter. You'll still get this same shape. But let's find out what the equilibrium solutions are. I'll set R times 1 minus n hat over K times n hat equals 0. So this tells me, well, first of all, let's get rid of that R. We'll just divide both sides by R. So at this point we have 1 minus n hat over K times n hat equals 0. So either 1 minus n hat over K equals 0 or n hat equals 0. So n hat equals 0 is one of the equilibrium solutions. It's the one where the graph crosses the vertical axis. For the other one, let's see, if I add n hat over K to both sides, I get 1 equals n hat over K, and then multiplying both sides by K gives me n hat equals K. So this one must be K. Putting the arrows in, we can see that the equilibrium solution n hat equals 0 is unstable, and the equilibrium solution n hat equals K is stable. The next example is basically a refinement of the logistic equation. The Alley effect takes into account the fact that sometimes when populations drop below a certain level, they then decrease to extinction. This might happen because, for example, if the population is too small, then individuals might have difficulty finding mates for reproduction. Once again, I've obtained the phase plot from GeoGebra by putting numbers in for R, A, and K. Let's find what those equilibrium solutions are. So we have R times n minus A times 1 minus n over K times n equals 0. And I should put the little hats on the ends because these are specifically equilibrium solutions that we're looking for. I'm going to get rid of the R by dividing both sides by R, at which point I have n hat minus A times 1 minus n hat over K times n hat equals 0. So either n hat minus A equals 0 or 1 minus n hat over K equals 0 or n hat equals 0. Solving these, we get n hat equals A or n hat equals K or n hat equals 0. So we can label our equilibrium solutions 0, A, and K. Now, how do I know which of the two non-zero ones are A and K? Notice that we were told that A is less than K. So that's how I knew to make the one furthest to the right K and the one in the middle A. putting the arrows in. We can see that n hat equals a is unstable because the arrows are pointing away from it. N hat equals k is stable because arrows on both sides are pointing towards it. And n hat equals 0 is also stable.